Hello everyone, and welcome to our first lecture on what is really the heart of Physics 1, which is Newton's laws. So we started out talking about kinematics, and now we're going to talk about dynamics. So we'll build on what we know about displacement, velocity, acceleration, and stuff like that. And now we'll move on to talk about the forces that act on objects and cause them to accelerate. So historically speaking, Newton's laws are really revolutionary. They completely transformed the way that we think about natural phenomena. Today, we tend to think about nature as obeying certain mechanistic laws, and that was really not the case prior to the discovery of Newtonian mechanics. They're central to your success in engineering education as well. So you're going to use these laws a lot, not just in this class, but in subsequent classes as well. So let's get right to it. Newtonian mechanics is incredibly powerful. It applies to the vast majority of human scale and even up to planetary scale physics, but there are some limitations on Newton's laws, so we'll restrict ourselves to the realm of Newtonian mechanics in this class. So that includes speeds that are much, much less than, say, the speed of light. Outside of that range, you need special relativity. Length scales that are much larger than molecules and molecular bonds and stuff like that. And, well, eventually we'll get on to talking about gravity, and we'll restrict ourselves to gravitational fields that are a lot smaller than those, say, that are near black holes, things like that. So otherwise you would need general relativity. So Newton's first law, then, I sometimes abbreviate Newton's laws N1, N2, and N3 for Newton's three laws. So Newton's first law says that an object in motion remains in motion, and an object at rest remains at rest unless acted upon by a net force. Okay, this is called the law of inertia, and it just basically tells us that accelerations, or changes in velocities, are brought about by forces, and a force is just a push or a pull. So an object in motion will remain in motion, and if I take an object at rest, say this object right here that I'm going to set down on the table, it'll stay there. It'll remain at rest unless I take an outside force and cause it to accelerate. So that's what Newton's first law says. Now, it's important to note that Newton's first law holds only in what's called an inertial reference frame. Okay, and basically an inertial reference frame is just one that's not an accelerating reference frame. So here's a helpful example for you. So let's say that you're driving and you set a cup of coffee next to you on the center console in your car, and you're driving at a constant speed. The coffee cup doesn't appear to be moving in your reference frame, right? Because it's in the car moving with you. So it appears to just be stationary from the point of view of your reference frame. Now that's when you're driving at a constant speed. If you then pull up to a stoplight and you stop, you'll accelerate down to 0, and that coffee cup might just slide forward and off of your dash and make a bunch of, make a mess for you. Now, in that particular case, that coffee cup appears to accelerate to you, but that's not because there was any force acting on it. You won't, in fact, observe any force at all that is acting on the coffee cup. So the thing will accelerate without a force being applied. And what accounts for this? Well, it's because this is a non-inertial reference frame. It's an accelerating reference frame that you're sitting in that accounts for this motion rather than an external force that's bringing about the motion. So somebody who's observing this, say, who's standing on the sidewalk, they will see an external force that was applied. It was applied to your car, but not to that coffee cup, which is what accounted for this motion, right? We try to restrict ourselves to inertial reference frames. It's possible to modify Newton's laws so that you can do them in non-inertial reference frames, but that's a more advanced topic. So whenever you're setting up your coordinate systems, your reference frames for your homework problems, their exam problems, make sure that you're always in an inertial reference frame. The most common example of a non-inertial reference frame that you see is like a spinning reference frame. So a merry-go-round, for example, the effect that you feel as you're spinning around in a merry-go-round or something where you're pushed out towards the side, that's the result of being in a non-inertial reference frame. Probably our most common reference frame in Physics 1, or the one that we use the most, is just at rest with respect to the floor or the ground. And so we treat that as if it's an inertial reference frame for the most part. But you should just, it's worth mentioning that technically the Earth does rotate, so you might have heard of the Coriolis effect. That's a result of the rotation of the Earth. In most cases, the rotation of the Earth is completely negligible. So the assumption that, you know, your room is an inertial reference frame is just perfectly fine, because any experiment that you do in the confines of your room is not going to need the rotation of the Earth taken into account. So anyway, unless you're otherwise told to do so, just neglect the rotation of the Earth. One more thing, so the statement again was, an object in motion remains in motion, and an object at rest remains at rest unless acted upon by a net force. Now that phrase net force there is key, okay? So if I take something, and I can take and push down on it and apply this force, to it, and it will not accelerate. And the reason is because this cup that I'm pushing on is also resting on a table. The table's pushing up on it. So when I apply this force here, I apply a force down, but the table applies an equal and opposite force pushing up against the cup that counteracts this force that I'm applying to it. So even though I'm applying a force, I'm not able to produce a net force because it's balanced, that downward pushing force is balanced by the force that the table uses to counteract my force. So an acceleration will only occur when there is a net force. Alright, so let's start talking about Newton's second law. Newton's second law says that the net force on an object is equal to its mass times its acceleration. So net force means we're taking the sum over all of the forces that could, over the potentially many forces that could be acting on an object. And this formalism here, the way that it's written, F net equals ma, is assuming constant mass. Okay, so really quick, if the mass of some object is changing in time, like say a rocket that's losing mass as it burns fuel, or a raindrop that's acquiring mass as it falls through a misty atmosphere or something, then it's technically F net equals the time derivative of momentum. But again, we're gonna wait until you get some calculus to express it that way. So the SI unit of force is the Newton, where a Newton is a kilogram meter per second squared. And note that we're talking about translational motion here. So there's no rotating objects, that we're not talking about rotation or any rotating objects, at least not until chapter 10 of the textbook, so not at this point. And this is a vector relationship, so it's important to note that each component of that equality holds independently. So the net component of force in the x direction is equal to mass times the acceleration in x, and the net force in y is equal to mass times the acceleration in y. So just a quick example. This is essentially a kinematics example that asks you to find the force. Nice little warm-up. So if you have a baseball of mass 0.15 kilograms and it's thrown from rest over a distance of 0.3 meters, and it gets accelerated to a speed of 30 meters per second. Let's pretend that this happens along one dimension. What is the average force that you have applied to the ball to accelerate it from that speed of 0 meters per second to that speed of 30 meters per second? Well, force in x then is equal to mass times the x acceleration. So we need to find the x acceleration. The kinematic equation that involves my known quantities, the final speed, the initial speed, and the distance over which that acceleration takes place, and connects it to my unknown quantity, the acceleration in x, is this one right here. I can plug in numbers then and solve for the x acceleration, and I get that the acceleration in x is 1500 meters per second squared. Then I can plug that in, multiply it by the mass to get my total force, and my force is 225 newtons. All right, on to Newton's third law. So, Newton's third law is sometimes stated for every action there is an equal and opposite reaction. It's probably better to say, if there is a force exerted on body 1 by body 2, then there is also a force exerted on body 2 by body 1. And that force is equal in magnitude and opposite in direction. So, okay, let's just say, let's just take the two objects to be my hand and the table. Okay, if I take my hand and I push down on this table here, I'm exerting a force down on the table. Then the table will exert an equal and opposite force up on my hand. Now, if I push down really hard, right, you can pick up my hand and see it's even white, a little bit white there. Okay, that effect on my skin doesn't come from the force that I exert on the table, right? That's from the equal and opposite force generated by the table pushing back up on my hand. Okay. Now, in vector notation, it looks like this. F12 equals minus F21. Okay, so the order of the indices here matters. F12 is the force on object 1 by object 2. Okay, so note that the two forces here are acting on different objects. F12 is a force on object 1. F21 is a force on object 2. Okay. You can easily see then that they're equal in magnitude since the only difference is a minus sign, and that minus sign also means that they're opposite in direction. Okay, a few examples. So rocket motion is a great example of Newton's third law. The rocket pushes down on the gases that it expels, and then the gases push up on the rocket because of Newton's third law. Similarly, when you're walking, you walk by pushing using your feet to push back on the floor. And then the floor also pushes you forward because of Newton's third law. Here it's the friction force that's mediating this whole thing. Now, let's just take a quick example. So if I have a ball and it hits a board here, right, say that it hits it and kind of bounces back off of it. Okay, now there you can see it's pretty obvious that you can see Newton's third law in action, right? This thing comes in, it's obviously going to exert its force on this ball, on this board here, right? It wasn't enough to accelerate it in this case because the other forces are keeping it in place. And the board then exerts a force back on the ball, and that makes it roll back, okay? So there was no acceleration in this case, right? Newton's third law is easy to see. Now I'm just going to move this thing that's holding it in place out of the way and do it again, okay? Okay, there was an acceleration, right? That thing slid back this way. Now, this is really important. Even in the case where there's an acceleration like that, Newton's third law still applies. If this thing exerted 25 newtons of force on that thing, then that thing exerted 25 newtons of force on this thing, even if they both hit and roll off in the same direction. It's still true. Okay, Newton's third law always applies. Now, it even applies with non-contact forces like gravity. So right now, the Earth is pulling down on me. Right? It makes up that's my weight. The Earth has this gravitational influence on my body and pulls me down. Okay, I am also pulling up on the Earth, right? So I am exerting a force on the Earth, and it's the same magnitude as the magnitude of the Earth pulling down on me. It's just that the 160 pounds that I am will actually pull me down quite a bit because my mass is so low. But my 160 pounds worth of force that I can generate on the Earth, which is massive, has absolutely no effect and will never make it accelerate at all. Okay, now, given that you know Newton's third law, I want you to just think about this for a second. How could you use your knowledge of Newton's third law to escape if you're stuck in the middle of a frozen, frictionless pond? So you can't walk because there's no friction. How are you going to use Newton's third law to escape from a frozen, frictionless pond? Okay, pause the video and think about it for a second. Okay, hopefully you thought about that a little bit. Now let's talk about it. Alright, so Newton's third law will be really helpful for you in getting out of this frozen, frictionless pond because all you need to do is exert a force on something in some direction and you will go in the opposite direction. Take your boot off and throw it in one direction. You will slowly accelerate back in the other direction. Now, how slowly? Well, So here's kind of the problem you'd have to solve to figure that out. So the equal and opposite force that is exerted by the boot on you after you throw the boot will go in this opposite direction here, and that means that the mass times acceleration can be set equal with that minus sign there. So if you divide then by your mass on both sides of this equation, you can see that the acceleration that you experience is minus the acceleration of the boot times this mass ratio here. Okay, now this is going to be a really small number, right? Because this mass ratio is really small. You weigh a lot more than your boot does, essentially. So you'll accelerate very slowly in the opposite direction.